All right, today we start a new chapter. This is an introduction to the normal distributions and the standard normal distribution. So basically, again, some definitions. The normal distribution is a continuous probability distribution for a random variable x. The graph is called the normal curve, and you can see a picture of it here. And it has the following properties. The mean, the median, and the mode are all equal. The normal bell shape is going to be the picture, so it's going to be normal bell shape. It's also going to be symmetric about the mean. There's our mean. The total area under the curve is equal to 1. The normal curve approaches but never touches this x-axis, so you can see it gets closer and closer and closer to the x-axis on both sides, but it never touches. And between plus and minus 1 standard deviation is where the curve starts sort of changing direction. I know that's a little hard to see, but basically we just need to know that at plus or minus 1 standard deviation is this point that we call an inflection point. So it's just the change in the curvature of the graph. All right. So then we get into what we call a probability distribution function. Probability distribution function, PDF. A discrete probability distribution can be graphed with a histogram. For continuous probability distribution, you can use a probability density function. The probability density has 2 requirements. Again, the total area under the curve is equal to 1, and the function won't be negative. So remember that probability, by definition, says that we have to have numbers between 0 and 1 inclusively. So we can't have negative anyway. We also can't have numbers larger than 1. So that's why the curve is going to be equal to 1 and never negative. So that follows the definition of a probability. All right. Means and standard deviation. The normal distribution can have any mean and any positive standard deviation. The mean gives the location of the line of symmetry. The standard deviation describes how the data is set. So again, we have a mean of 3.5, standard deviation of 1.5. So if we were to graph this, now the graph is already shown to you, but just so that you sort of have an idea, it's going to be bell-shaped. The mean is in the center. It's going to be our mean. The mean in this case is 3.5. Because the standard deviation is 1.5, then at about this point of inflection on both sides of the curve, we're going to add 1.5 and subtract 1.5. So 3.5 plus 1 standard deviation would put me at 5. 3.5 minus 1 standard deviation would put me at 2. So again, I'm going to add 1.5 here. I'm going to subtract 1.5 here. And I can also do that for the next part. So my second standard deviation then would be at 6.5. Back here at 0.5. So I should be able to draw my graphs just based on where the standard deviation fits in connection with the mean. So likewise here, the mean is 3.5. So again, we're going to start at 3.5. But this time I'm only adding or subtracting 0.7. So that's going to make this picture much steeper. So a smaller standard deviation makes your curve steeper. So larger standard deviations are going to spread it out more. Shorter standard deviation is going to make it steeper. And remember that if I'm writing SD for standard deviation, that's also the same as we use for sigma. So understanding the mean. Again, we talked about this. Which one has the greater mean and which one has the greater standard deviation? Well, here, my mean for B would be 12. On this one, my mean is 15. So obviously the curve with the greater mean is curve A. But as far as standard deviation, this one, right about here and here are my points of inflection versus here and here for my points of inflection. And so you can see again, steeper would have smaller standard deviation. And you can also actually count this one too, because it's set up a little easier to count. This one looks like my standard deviation is 3. Where this one, the standard deviation doesn't get anywhere near 12 or 18. So this time my standard deviation is probably more like 1.5 maybe. So the curve with the greater standard deviation should be curve B. Interpreting graphs of normal distributions. The scaled test scores for New York State Grade 4 Common Core Assessment are normally distributed. Oftentimes, that's going to be the case. A lot of the data we look at ends up being normally distributed. So we notice that it's normally distributed. The curve is below. What is the mean test score? And estimate the standard deviation. So if we try to find right in the center, it looks like my mean score is going to be somewhere right in here. If I look at the scale of this, it's about every 10 units. So my scale is going to be somewhere between 280, 290, 300, 310, 320. So somewhere around 305. So my mean is estimated to about 305. Now my standard deviation, again, is going to be sort of, let's see, if you kind of look at the whole curve, it's going to be sort of halfway between. And remember, it's symmetric, so it'll be the same on both sides. And so if we start looking at that standard deviation, we end up being somewhere right about here. So it looks like my standard deviation is approximately, say, 40, 10, 20, 30, 40, 10, 20, 30, 40. So it's approximately 40. And then one of the nice things, because this is standard, now we can take a look at the fact that about 68% of the data is going to fall within one standard deviation. Between two standard deviations, 10, 20, 30, 40, and 10, 20, 30, 40. So this would be my two standard deviations, and this is going to include about 95% of my data. So the student scores in this case, 68% would be between, if we're looking at the standard deviation, so if I add 40 here, we have 345. If I subtract 40 here, we end up with 255. I'm sorry, it's 365. Right there, I can read a little better. 265. So about 68% of the students will have a score that is between 265 and 345. About 95% of the students will have a score between 225 and 285. So that gives you a really good range of where the students should score. Meaning, if they score here, they're really below what the sort of average would be. Likewise, if they score here, they're really above what the average would be. And only a couple percent of the students are going to fall here, and only a couple percent of the students will fall there. Because remember, we only have 5% to work from. So that means that we'd only have about 2.5% of the students that are around 3 standard deviations above or below. So not very many students are going to do that. So what does the standard normal distribution do? Well, the standard normal distribution says we are going to take our curve, our normal distribution. We're going to end up with a mean of 0 and a standard deviation of 1. So the mean is going to be 0. The standard deviation is going to be 1. So basically, what we're doing, I don't know whether this is going to work, so we're going to try it. Basically, what we're doing is we're going to take any data, this is real data, I don't think that's going to work, any real data, and we're going to take it and transform it. So we're going to sort of overlay it. No, I'm not going to be able to do that. Overlay it so that it converts between the two. And it's just going to allow me to use my calculator. So that's one of the nice things about doing this. So basically, it's going to take this whole curve right here, and it's going to lay it on top of the rest of the curve. Okay. All right. The total area under the normal curve is still equal to 1. So we can still look at plus or minus 1 standard deviation, plus or minus 2 standard deviations. The area now is still 1. The mean is going to be 0. So what we do then is we're going to take any x value, any data point. So any data point. And we're going to convert it to this z-score, what we call a z-score, so that I now can use my calculator. All right. So again, this just talks about the fact that your z-scores are going to be close to plus or minus 3.49. Half your z-score at exactly the 0 point is also going to be 0, so that's about 50%. So when the z-score is 0, we're at about 50% of the students, and the area increases as the z-score increases. which should not be pterodoxopexy. All right. So there are a couple of ways then that we can find these z-scores, but before we can do that, we need to also see how to calculate this without a calculator, how to sort of put all these pieces together.